Hey Ross, let's look at what is happening in example 2 of 7.5. So we've got a standard form equation of a line in R2, and we're asked to find a vector equation. We did this in two ways on the lesson, in the printed lesson. I'll take you through a third way that I think is really important for dealing with planes. So what would a grade 9 student do? A grade 9 student would probably convert this to 2y equals x minus 3 or y equals 1/2 x minus 3 halves. They would then probably plot a y-intercept of -3 halves. That is us going 3 halves of a unit down from the origin on the y-axis, and then from there rising in the ratio of 1 to 2. Okay. Another grade 9 student might actually calculate the intercepts. They would set x equal to 0 and find that y is -3 halves. They set y equal to 0 and find that x is 3. You just connect the two intercepts and there's your line, which I'll label as L1 now. Well, what we can use now is the normal. So my grade 9 students are often curious in the format ax plus by plus c equals 0, which I stressed to them, and I stressed to my calculus students at the start of the year, is an important format. It may not be useful yet, but it's necessary to deal with vertical lines. That was the only reason that I had back then, I suppose, in grade 9. They often want to know, what does A represent, and so what does B represent, and what does C represent? Well, we've discovered that like A on its own still doesn't really represent much, but A and B now we have an interpretation of. I know that A normal to this line is given by 1 comma -2. I'm not going to hang on to the significance of this -3. You can call it the constant of the line. It's related to some point on the line. It's not always going to be the opposite of your x-intercept. That's only if this coefficient is 1. It's not always the numerator here. That's, again, a kind of a coincidence in this situation. If you want to see that normal, I don't know, let's draw it from, I suppose we could draw it from the origin. You go over 1 and down 2, and your vector would look something like that. Notice that it is perpendicular to or normal to your line. It might make more sense to actually draw it originating from your line. So here is a vector that goes right 1, down 2. That is a normal vector there. We could also use, the reason why we talk about lines having two unique unit normals is because we can go in the other direction on this line. Neither one of these is a unit vector, but they have, I guess it's like the sort of simplest form of these vectors. Let me call that normal 1. I could call this normal 2 is -1 comma 2. And I'm not crazy about it because it has a leading negative, but it's acceptable. I mean, I could also use any scalar multiple of this. So there's not one unique normal, but there is a unique normal line, let's say, one family of lines that is perpendicular to this. Okay, the next thing I want to talk about was the importance of using different parameters. If I wanted to show to you that the two vector equations that I came up with, which were, sorry, I actually haven't done that yet. I guess if this is my normal vector, I might just sort of do this graphically or visualize it here. Then I could use a direction vector of 2 comma 1. And then I think for one line's definition, I used 0, -3 halves plus s 2 comma 1, where s is every real number. And I think another definition that I used was 3 comma 0 plus t 2 comma 1, where t is every real number. So if I wanted to show that these two lines are coincident, I would have to convince a reader that their the system of equations has an infinite number of solutions. And if these parameters are the same, I'm doing that by default. I'm making sure that that happens. And that's not what I want to happen. I want there to be an infinite number of s and t values that will give me coincident points for these two lines. So very, very important to use different parameters. Okay, option number 3. which I want you to try out at least once in the homework, because it really comes in handy with planes, is you set a parametric value. Um, I Let's say set a parametric definition instead, because it's not really a value. So in the equation, x equals -2, y minus 3, trust me on this the first time through, I need to choose a different parameter. I'm going to set y to be u. I'm just going to let the value of my parameter be the same as the value of my outputs, sorry, I shouldn't be talking about inputs and outputs when I have a parametric equation, of my y values. What I'm doing here, it might seem like I'm taking an awful lot of liberty, but what I'm doing is actually saying that I want to use something, comma, 0 as my R0, and something else, I guess, just another question mark with the subscript 1, comma 1 as my direction vector. I'll point this out later when we get to the parametric equation, the consequences of what I'm doing. But it seems like I'm taking an awful lot of liberties here, but I'm actually making 2 decisions and then just finding the consequences, discovering the consequences of those decisions. So if I set y equal to u, I can say then x minus 2u minus 3 is going to equal 0, which means that I'm going to isolate for x now. X is going to be 3 plus 2u. I'm just going to take this statement right here and write it out as y equals, I'm going to put in the invisible 0 in front and the invisible 1 as well, my 2 identities, identity by addition and identity by multiplication. And there you go. There is my discovered R0, 3, 0, and here is my discovered direction vector, 2, 1. Now, it turns out that me using a different parameter turns out not to be necessary, because I think I'm going to find the exact same equation as I found up here with t. That's okay. My value of u will just always be equal to this person's value of t. So these are my parametric equations. Where am I going to say that u is any real number? Probably up here, or maybe in my conclusion. Then the definition that I have for this line is that some known point on the line is 3, 0. And then I have an infinite number of scalar multiples of the vector 2, 1. Okay. It comes into place really sort of smoothly in a kind of neat, elegant way. Now I've chosen to let y be the value of my parameter just to avoid some fractions. Maybe I'll just go through this one more time and give you a fourth, or technically third, unique equation. Actually, it might not be. I think I'm going to get the exact same equation as up here if I set x to be my parametric value. Let's find out. So option 4. I am going to set, I'm running out of letters though, xbw, where w is any real number. Okay, I'm allowed to do this because what I'm deciding is saying basically that I want my position vector to have an x component of 0 as opposed to a y component of 0, and I want my direction vector to have an x component of 1. So no, it's not quite going to be the same. I'll have a fraction here. If I let x be w, sorry, I just need to see my original equation up here, then I'll communicate that, and please show this work to your reader, because this is, it can be a challenging solution to read, which is why I wanted to walk you through it. Then w minus 2y minus 3 will equal 0. Let's help our reader see this by rearranging for them. 2y is going to be w, let's change our order there. I like the constant first, minus w. That means that y is going to equal, let's give ourselves another line of space here. Y is going to equal -3 halves minus 1/2 w. Right above that, I think I'm going to put in x is going to be 0 plus 1 w. And I like doing this right on top of each other, just like I did right here, because there are the components of my position vector, and there are the components of my direction vector. So my definition for this line is going to be r equals Let's use 0, comma, negative 3 halves as some point that's on the line. That sounds familiar. And then I will add w scalar multiples of a direction vector 1, comma, negative 1 half. And while it would be nice if our direction vectors were always integers, it's not always possible. And I don't want you stressing out about it. Like, you shouldn't actually just multiply this. You can't change this to 2, negative 1 and expect that w to be the same. You would just introduce a new parameter there. There is actually no formatting issue with this fractional component here. You're allowed to have fractional components in a vector parametric equation. Okay. Practice the approach. It takes a little convincing to get students to try it, but it's really, really useful when we're working with planes, which we will have a chance to do later in this course.